Our topic is talking about an electric dipole. An electric dipole is a pair of point charges with equal amount of magnitude and an opposite sign, one being a negatively charged and the other is a positively charged. The two charges are spaced at a distance d, and these charges will interact each other. That results a kind of field. So the field is known as an electric dipole field, wherein the field is outward from the positive and it is inward in a negatively charged. One of the property of the electric dipole is a kind of electric dipole moment and symbol P, and this is a vector quantity, and this measures the strength of the dipole. The direction is coming from negative towards the positive. If we place this dipole in an area wherein it has a constant electric field, the dipole will rotate, which means that the dipole is not in an stationary state. It will keep on moving. So what will be our objective for this module? First is to define the electric dipole moment, and we will calculate the magnitude and its direction. The next, we will quantify the amount of rotation, torque. Then after that, we will compute the work done on an electric dipole. Then finally, let's derive the relations of electric potential energy of this electric dipole moment. Now, why we need to study an electric dipole? The answer is electric dipole moment is very important in our everyday life because we always use water, and water is a kind of an electric dipole. It has two oxygen, two hydrogen, and one oxygen. The the hydrogen, the total hydrogen charge is the same as the charge on the oxygen. The oxygen is negative while the hydrogen is positively charged, and they are spaced at a distance d, which means that a water molecule with the presence of electric field is keep on moving, rotating its axis. Oxygen will stay on the hydrogen because of the strength, which is the electric dipole moment. So, if we have an electric field, a constant electric field, and if we place the electric dipole, then this dipole is subjected with a force because the charge will experience a force because of the presence of electric field. Both negative and positively charged experience a force due to the constant electric field. By definition, the force on the positively charged is equal to the product of the charge magnitude and the electric field. And the direction of the force is the same direction as of the electric field because this is a positively charged. Meaning if we multiply this one to the electric field, the result is positive. Positive means it is the same direction with the electric field. But if we if in the negatively charged, the force is a negative force because if we multiply this negatively charged to the electric field, the result is negative, which means that the force on negatively charged is in opposite direction with the electric field. Now take note that this charge, negative, is the same as the charge in the positive, which means that the two forces, force on positively charged and force in a negatively charged, are the same, but in opposite direction. Which means that if we sum up the two forces, the result must be 0. In other words, for every electric dipole, the electric force is 0. But it won't stay, it won't at rest. In this case, it's because that the two forces have a torque arm, which means that this will rotate in the direction of a clockwise direction. This force will tend to move in this direction, while the other this direction. So therefore, the tendency of the dipole is to rotate in a clockwise direction because of this distance d. So that will be the resulting effect because of the force. The question is how much is the torque? Now take note that this dipole has an angle coming from the electric field. So this angle P, is the angle from the electric dipole moment or from the electric field towards the dipole moment. So it has a torque arm with the amount of d sine P. It's because that we have this d as the distance between them and we have the angle P coming from the electric field. So this opposite side is d sine P. So how much is the torque? What will be the amount of rotation? Now torque is defined as the force times the torque arm. Meaning this is the force and this is the torque arm. If we multiply these two values, then the result is a torque. QE being the force and d sine theta is the torque arm, TP. Yan. If we rearrange this one, the Q, the product of Q dE sine angle P is the magnitude of torque in the direction clockwise. So this vector quantity, the electric dipole moment, has an angle from the electric field with the amount of angle P. So therefore, because of the presence of the angle between the electric field, the dipole will rotate. Now notice that this angle is keep on reducing until arrive at the direction of the electric field. So we can say that the torque is a negative torque because it reduces its angle until 0. Now quantifying the amount of how much is the strength of this electric dipole. If we multiply the charge by this distance, the result is the magnitude of electric dipole moment. And the direction is from negative towards the positive. The water molecule has a dipole moment of 6.13 times 10 raised to the negative 30 coulomb meter. The unit is coulomb meter because coulomb is for the charge and meter is for the distance. So, looking at this statement, the torque is QDE sine P. QD is the electric dipole moment. So, meaning we can replace this one with the dipole moment, resulting the magnitude of the torque as the dipole moment times electric field times the angle P which angle P is the angle between these two vectors, then the result is the magnitude of the torque of an electric dipole. Now, since this is the magnitude of vector dipole moment, and this is the magnitude of the vector electric field, and this angle is the angle between the two vectors, then by principle of the cross product, torque becomes the P cross E, meaning the cross product of this dipole moment and the electric field is torque. Now, if we calculate the work done, how much work done is produced by the electric dipole? Then, the result is the product of the torque and the angle. If you multiply the amount of rotation by that angle, the answer is work done by the electric dipole. Now, since this is an infinitesimal angle multiplying by the torque, the result is the infinitesimal work done. So integrating these both sides, now take note that the torque is a negative torque. Why negative? It's because that this angle is keep on reducing until zero as the dipole rotate towards the positively or towards the direction of the electric field. So torque must be a negative torque because the angle is reducing and reducing. So substituting this value to the formula of the work done, then the infinitesimal work done is negative PE sine angle P D angle P. So integrating both sides, work done by an electric dipole is the integral from angle P1 to angle P2 of negative PE sine angle P D angle P. So evaluating the integral, because the P and E are constant, so we can place this outside, leaving the negative, or bring it the negative outside also. And the integral of sine P, angle P, is a negative cosine. So negative, negative, and the negative integral of sine P is positive. So we come up, after integrating, work done is PE cosine angle P. And the limits of this angle is coming from angle P1 to angle P2. So evaluating the limits, upper minus lower, then this is the result. Meaning, if we calculate the work done, it is just the product of the angle P times the cosine of the angle, the final angle, minus the P E cosine of the initial angle. Now, where is the initial and where is the final? Now, in this case, the angle starts from this point. So, this is the initial angle. So, this is angle P2. Now, in the final situation, this moment, electric dipole moment, will stay in this axis. So, then, this will be our angle P2, which happens to be 0 in this case. Okay? So, this is how to calculate work done. And take note, PE are common, so we can take it out. Or, by definition of electric potential energy is the product of P. So, which means that this one is a kind of electric potential energy. This is the initial potential energy, and this is the final potential energy of the dipole. So the electric potential energy defined as the negative PE cosine angle P. Why negative? Because the angle is keep on reducing until zero. So the potential energy must be a negative value, which means that again this is the electric potential energy final and this is the electric potential energy initial. The difference is a change and this is negative. So therefore we can say that the work done by an electric dipole is a negative change in electric potential energy. Now notice again that P and E are the magnitude of two vectors and they are spaced at an angle P. Now this is cosine, so therefore this must be a dot product. You recall the principle of vector analysis. The cosine is dot product, while the sine in the torque, this one, is a kind of a cross product. So these are the definitions of the important quantities on the electric dipole. The electric dipole moment as P Q D. The torque of an electric dipole moment is the cross product, the P cross E. And it has a magnitude of PE sine P, while the work done by the electric dipole is the change in electric potential energy. This is the potential energy final and this is the potential energy initial. Subtracting the two, the result is work done. And the electric potential energy by definition is the negative dot product of P dot E. And it has a magnitude, or we can transform this one into a kind of negative PE cosine of the angle P. This is the principle of electric dipole. So in order to understand clearly the situations of an electric dipole, consider again the electric field, and if we place the dipole moment in a perpendicular orientation with the electric field, which means that the angle between the dipole moment is 90 degrees. The question is, what will be? What will happen to the electric dipole moment? Now notice that positive force is towards electric field. In the negative charge, the force is opposite to the electric field. So therefore, and the angle, the dipole moment is coming from negative towards the positive. So the angle between them is 90. So therefore, this dipole will tend to move in that direction. And it will rest on the electric field direction. Which means that this is the stationary state of the dipole in the presence of electric field. And in this case, the angle between the electric field and the dipole moment is 0. So this will tend to at rest. Now what will happen if we change the configuration of the electric dipole? Suppose this is now the positive and this is the negative charge. And this is the dipole moment from negative towards the positive. And this is the electric field. So notice that the angle is greater than 90 but less than 180 degrees. So the question is, what will happen to this electric dipole? What will be the rotation? Is it the same direction as previous? The answer is yes. But the amount of rotation is different from the previous. Why? Because the angle between the dipole moment and the electric field is greater than 90 degrees. So the amount of torque will increase. So if take note that the positive is the charge has a force that tends to move in the direction of the electric field because this is a positive charge. While in negatively charged, the force is tend to move away in opposite direction of electric field. So therefore, the tendency theoretically of this dipole will tend to move in a clockwise direction. So that this will be the resulting. So this dipole will rotate until such time that the dipole moment will rest in the direction of the electric field. So in this case, this is an stable state, stationary state of the dipole. Now, suppose this is the position of the dipole. What will be the direction of the rotation? Very simple. Again, this is the positively force on the positively charged towards the direction of the electric field, while the negatively charged, it is away from the electric field. So, the rotation now is different in the previous because this is rotating counterclockwise. So, this will be the result. Okay? So, it will rest again when the dipole moment is in line with the electric field. Now, what will happen if we have this position wherein positive and this is negative? So, the dipole moment is already in line of the electric field because this positive is towards the negative is opposite. Again, if you sum up 0 and there is no angle between the magnetic dipole moment and the electric dipole moment and the electric field. So therefore, there is no rotation in this. So meaning the electric dipole is just like a spring. If you stretch the string, then release, it will return to its position. In the electric dipole, if there is an angle between the dipole moment and the electric field, then the rotation will rotate the same direction as the angle between the dipole moment and the electric field. Which means that if there is an angle between the dipole moment and electric field, the electric field is not in a rest position. Now, in order to understand the application of the electric field, let's have this example. This is the figure. Given the magnitude of the charge, be equal to 1.6 times 10 raised to negative 19. So this Q is 1.6 times 10 raised to negative 19 coulomb, and this charge was placed on the uniform electric field of 5.0 times 10 raised to 5 Newton per coulomb, and the distance between the charge is 0.125 nanometer, which is equivalent to 0.125 times 10 raised to negative 9. And given the angle of inclination of the dipole, 35 degrees from the electric field. Now you are asked to find how much net force exerted by the field on the dipole. How much force? In letter B, you are asked to find the magnitude and direction of the electric dipole moment. Now, in this case, the dipole moment, take note, is coming from negative towards the positive. How much is that magnitude? In letter C, you are asked to find the magnitude and direction of the torque. And finally, in letter D, you are asked to find the potential energy of the system in the position given. So to answer this problem, all you need to do is for letter A, you are asked to find the net force. And we understand that these two charges are subjected with a force because of the presence of the electric field with a magnitude of 5 times 10 raised to 5. So, force on charge, positive charge, is towards the electric field, and it has a magnitude of Q times E. While in a negatively charged, the force is opposite to the electric field, and the magnitude is Q times E. So the same magnitude but in opposite direction, then it follows that the total force on the electric dipole is zero. Again, the total force on the electric dipole is always zero. For the reason that they have opposite charge. That's why we call this as electric dipole, because the total force is zero. Now, letter B. What is the magnitude and direction of the dipole moment? Now, take note by definition that the dipole moment P is the product of the charge and the distance between the dipole. So, substituting the given, Q is 1.6 times 10 raised to negative 19, while D is 0.125 nano, equivalent to a meter of 0.125 times 10 raised to negative 9. Substituting that values, and it gives us 2 times 10 raised to negative 25 coulomb meter. So this is the answer for letter B. Letter C, magnitude and direction of the torque. How much torque will rotate and what is the direction? So look at the figure. You are asked to find the okay. So by the way, the direction of the dipole moment is always towards the positively charged. In letter C, you are asked to find the magnitude of the torque. How much is the magnitude and what is the direction? So look at this one. The dipole moment is coming from negative towards the positive, and this is the electric field direction. Now, where is the angle P? Because the formula for the torque is P E sine angle P. So your P is the answer in letter B. Your E is given as 5 times 10 raised to 5. How much is the angle between the two? Is it 35? Is it the given in the problem? 35? The answer is no. Why? Because what is P again? P is the angle from the electric field towards the direction of the pointing the direction of the dipole moment. And this is the positive side is the angle the direction pointing the electric dipole moment. The dipole moment is coming from negative towards the positive. So the angle must be from here towards this one. So this must be what? This is 145 degrees. So, reminders, do not use the 35 degrees because 35 degrees is not the angle from electric field towards the direction pointing the dipole moment. So, take the complementary angle of 35. That's it. That's the angle P. So, substituting the value, or in order to make it clear, this is the direction of the electric field and the angle must be coming from the electric field, and it will end up to the pointing direction of the magnetic dipole moment. So the angle must be 145 degrees. Substituting its values, that comes up with 5.7 times 10 raised to 24 Newton meter. This is the unit of torque. And reminders, you cannot change this into a joule because this is torque. Torque, the unit must be Newton meter. In letter D, final question, you are asked to find the potential energy of the system. So you have to recall the relation that the U is a negative PE cosine angle P. Substituting the values again, because we have already P given the value of E, and we have obtained the amount of the angle, which is 145. So substituting the value and calculate it, the result is 8.2 times 10 raised to 24 joules. The resulting unit of this, because this is coulometer, sorry, this is electric field. You have to change the, this is this is the dipole, okay, then the electric field must be this one, so you can erase this one. This is not included, so this one multiplied by 5 times 10 raised to 5 cosine of 145, the result is 88.2 times 10 raised to 24. So this is not included again. Eliminate this one, and the result is 8.2. And these are the answers to the questions and basic dipole. Thank you very much.